I introduced the reaction quotient, Q, on Friday in class, and now it's time to do some problems with it. So the problems will always be the same, and you should be able to do them in an exam with your pocket calculator. So I'm giving you a reaction here, it's very abstract. Then I'm giving you the concentrations, and then you have to calculate Q. So this is the mnemonic. You have to take the product concentrations and divide it by the reactant concentrations. When we implement this, we have to pay attention to the coefficients. So if there's a coefficient that is not 1, then we have to square or cube our concentration in the relationship. And then the other thing is, if the concentrations are in molar, we just drop the m because we don't want to have any units for Q. If they're not in molar but in millimolar, then you can first convert them and then drop them. Okay, so I'll just show you in PQCalc how you would do this. So you would take Q is equal to, and I'm going to be careful and put parentheses around the top and the bottom of the fraction just to make sure. So the product is 2 C's, so we take this concentration here, but it has the molar on it, so I have to drop that, so 0.5, and then to the power of 2. Oops, that's not the power, to the power of 2. So that's all products, and then we divide it by a big fraction with all of the reactants. We have 3 A's, so we have to take the 0.14 molar, drop the molar, and then raise it to the 3rd power, or cube it. And then we have to multiply it by the concentration of B. Here that's just the concentration of B without the molar, because there's a stoichiometric coefficient of 1. Let's just make this a bit cleaner. So just some problems that people run into. There's a plus here. Don't write a plus here. You have to multiply all of them with each other. That ensures that if one of them is 0, you know that you're not at equilibrium because all species have to be present, so the Q will become 0 or will become infinity. The other complication is things that are not in solution. We'll get to that in the other examples. Okay, so I can send this off. You can see this is on top, this is on the bottom, as it should be. The top gets to be 0.25, the bottom is a little bit smaller, and then we get this odd way of writing it, but that's just 8. No, it's 80, sorry, it's 80. It writes it like that because of significant figures. So let me just give a couple more significant figures so that it's not so ridiculous the way it writes it. So now I have 3 significant figures everywhere, and hopefully, yeah, it has a more accurate value of 76. Okay, this is a little bit cumbersome, and this is sort of a rote calculation. So I want you to be able to do this on paper with a calculator, so you have to practice it. And B, I want you to have a fast way of checking your work, and that's why I give you this reaction slider. I made the specifications and gave them to AI, and the way this works is you just say, well, I have 3 A's plus a B react to, and the equilibrium error you write by writing a smaller sign, an equal sign, and a larger sign. Reacts to 2 C's. That was our reaction. If you don't write any physical state here, then it assumes it's a aqueous solution. So once I set this up, it has a space here for initial concentrations, and then it will calculate Q down here. So I don't remember what I had here. So A was 0.14, 1.2, and the last one, C, was the concentration was 0.5. Okay, and This calculator doesn't know about significant figures, so it gives you a ridiculous number. Here is abbreviated the formula, so you have to square the 0.5 and then you divide it, and I wish they had parentheses around it, and maybe I can fix that later. But you have to take the concentration of A and cube it times the concentration of B. So that's a quick way to check it. Just some things to be careful about. It has a switch for millimolar. Then this is interpreted in millimolar, and then we actually get a different answer. So make sure you're in molar. And in general, the safest thing is to calculate everything, translate into molar, and then go ahead and plug things in. This was written by somebody who has a very kind of, I don't know, male aesthetic, I guess. If you want to see it better, you can toggle this, but then you don't get the colors. So it's up to you. If you want to print something, if I ever ask you to print something from the reaction slider, put it on, what's it called, daylight mode, so you don't waste toner. And it's easier to see. Okay, so let's do 2 questions, and then I'll give you another 2 questions you can try on your own. So today's assignment or lesson is all AI driven. So this was written by AI, and I also got some questions to look at. Will this work? Yes, here are my questions. Okay, so I have a couple of different problems here. The precipitation one is interesting because it has a solid in there. Otherwise, some of them use millimolar, so be careful there that you're consistent with your units. And this might actually be a reaction that you're doing in lab, if we ever have lab again. Okay, so let's start out with the precipitation reaction. So the way we would set this up here is you write in the equation. So we have AgCl, and that's a solid, and that's important now because solids are treated differently in the reaction quotient. And then this is the equilibrium error again, so less than sign, equal sign, greater than sign. And then we're doing Ag plus. The charges you can just write on the, if there's only one charge, you can just write it behind it, and it's going to typeset it properly. Plus chloride. Okay. Then, sorry, wrong button. There we go. So this is having trouble with the plus sign. I have to check if I can fix that somehow. Yeah, this doesn't look good, but it's going to work like that. Sorry about that. What you can see is that the HECl is written as pure. We can't put anything in there, and that's good to know. It doesn't matter if we have a lot of silver chloride precipitate or a little. It doesn't affect the reaction quotient. And that's why it's not given here too. So that's another hint. Okay, then the silver concentration is very small. You can enter things here with an E, which is weird. It's not really E, it's 10 to the minus 5 or times 10 to the minus 5, but that's how old calculators did it, and so we still do it like this in some spreadsheets, do it like this, scientific notation, and this one does it too. Okay, and the other one is 2.0, E minus 4. Again, we can drop the molar like it. this because it's in molar already. If it were in millimolar or in some other unit, we would have to convert to molar first and then drop it. Okay, this is all done. And we get 3 times 10 to the minus 9. So Q is very small. Okay. So what did we have to pay attention to? The silver chloride is pure, so we don't have a concentration for that. Oh, here's our formula, right? So what we do is we take the two products, multiply the concentrations by each other, and then we divide by 1. If it were in the opposite direction, you would have 1 divided by. So don't forget the 1. If there's all solids in there as reactants or products, you write 1. Okay, next one is redox. And I'm going to probably run into the same problem again. Let's see. So I have copper as a solid. You already know what happens there. Plus 2 silver ions. And I'm just going to write them like this and hope for the best. Yep. So I can leave out the AQ and then I don't run into the problem. But I still want to fix that, make a better tool for you. If you have 2 positive charges, and I just write 2 plus, then you get the wrong thing, right? You see this is copper sub 2 plus, so I have to put a caret on top, one of these guys. And this looks good. Plus 2 silver as a solid. So we have 2 solids here, right? They don't appear in the equilibrium equation, but we have to specify what the concentration is of silver ions, and we have that as 10 millimolar. So the quickest way of turning millimolar into molar is to say 10 to the minus 3. And same for the copper. The copper is given as molar, so I can write 0.05, and then it should work out. Okay, and the answer is 500. What do I have to do? I have to take the copper concentration, which is the product, right? The copper ion concentration, drop the molar, and there's only 1 of these coppers, so that's it. And then divide by all the reactants. I have 2 silver ions, so I have to take the silver ions squared. Quickly want to show you, it also gives you millimolar, so let's keep in mind the correct answer is 500. I'm going to switch to millimolar. That will break the whole thing because these are not in millimolar. So then I can say 10 millimolar here, and I can translate the 0.050 molar into 50 millimolar, and then I still get 500. But again, I would just stick with the molar and call that 10e minus 3. And this one I would call 0.050. I could have also said here 10 millimolar is 0.010. Okay. If you're unsure how to do the conversion, you can check them in PQ Calc. Let's see if I can get a new page here. So if a concentration of silver plus is equal to 10 millimolar, then you can say, oh, I want this in molar. And then it says, yeah, that's 0.0100 molar. Or if you, yeah, that's fine. You can keep it like that. On the other hand, let's do the copper 2 plus. Again, we can practice. If we have a charge of 2, we have to put the caret up there to write it properly. So that was 0.050 molar. And then I can ask the question, what is that using millimolar? And so it will be 50 millimolar. Why do we even use 50 millimolar? Because in the lab, it's much easier to say, oh, this is a 2 millimolar solution, this is a 5 millimolar solution, instead of saying it's 0.002, it's 0.005. The zeros can go, you can miscount them. You don't know if you said 0.0 or you said 0.0. So it's very confusing, and it's easier just to switch to millimolar if you have concentrations that are in that range. And of course, there's lower concentrations like nanomolar, micromolar, picomolar, femtomolar. But usually we're in the millimolar range or in the micromolar range. Okay, so this were two examples of calculating Q. I want to quickly show you something that helps us with the next step. So let's make this a little bit brighter. The question is, what happens if the reaction proceeds now? So what happens if some of the copper and silver ions turns into copper ions and silver, elemental silver? Means the reaction goes net forward. In my table here, if it goes forward, these changes would be positive, these changes would be negative, because I'm using up silver and I'm making silver ions and I'm making copper ions and elemental silver. So there's a slider here. So you can change those concentrations as if the reaction were happening. So I can say, oh, maybe I want to increase the copper ion concentrations by a factor of, I see what's happening here. This is a rounding problem, I hope. Yes, yeah, that makes sense now. By 3 millimolar. So I just switched to millimolar, right? Because that's easier for me to say. And then this should go down by 6. So what happens then? In this fraction, the copper now is larger and the silver is smaller. And so we're going from 500 to 4,000. So keep that in mind. If the reaction goes forward, Q increases. Let's go back to where we were. And if I go backwards, so in this case, let's say I'm using up, of the 50 millimolar, I'm using up 30 millimolar by going backwards in the reaction. At the same time, I'm going to get 0.060 increase in silver in the reactant. So I was going backwards, I was sliding in this direction. My Q goes down. So very simple statement. If the reaction goes net forward, Q increases. If the reaction goes net reverse, Q decreases. So I encourage you to do the other problems. Let's see if I can find my problems again. This is an acid base, straightforward in terms of the all species being in solution, so they all count. The only little bit difference is here, this is in molar, this is in millimolar. So you can rewrite this as 0.0012, 0.0012, and then you could just plug it in there. We did the presentation and the redox, and the compensation here is straightforward. Everything's in molar, and coefficients are all 1, so that makes it easy too. And they're all species are in solution, so they're all given. As a concentration, there's nothing pure here. The only slight thing is you have to practice putting in scientific notation. And we can practice that in class too. I encourage you to bring your calculator to class every day from now on. The equilibrium unit is fairly quantitative, so it's good to have a calculator and to use the calculator that you will use later on in the exam. To get over technical snafus like entering a scientific notation number or making sure you have parentheses when you do a fraction. So that's actually the case here. So you have to take this product concentration and divide it by these two, the product of these two. So you have to put parentheses around them. Or you can use pqcalc, and then you see that you're getting the right fraction. But in the end, you have to be able to do it on paper with a pocket calculator. Okay, thanks for listening.